Everybody, like usual, we are going to take one medium question and try to pick one randomly. Oh. So this is a medium question, right? And you're given a binary string s and a positive integer k. A substring of s is beautiful if the number of ones and zeros is exactly k. Let length be the length of the shortest beautiful string. Return the lexicographically smallest beautiful substring of string s with length equal to len. If s does not contain a beautiful string, return any empty string. A string A is lexicographically larger than a string B if the first position where A or B differ, A has character strictly larger than the corresponding. Okay, ABCD is lexicographically larger than ABCC because the first position they differ is the fourth character and D is larger and greater than C. Okay, so let's read this one more time. You're given a binary string S and a positive integer K, right? A substring of S is beautiful if the number of ones is exactly K. So we're going to be given a string of binaries S and then an integer K. And S is beautiful if the number of ones in S is exactly K. Let len be the length of the shortest beautiful substring. Len be the length of the shortest beautiful substring. So there are going to be a lot of beautiful substrings, right? It's not a lot of beautiful substrings because all of them are going to have length K, right? Let len be the length of the shortest beautiful substring. Okay. So now we have the substrings and then we have the beautiful substrings. Okay, so a beautiful substring of S is one that the number of ones is exactly K. Let length be the length of the shortest beautiful substring. Okay. Return the lexicographically smallest beautiful substring of S with length equal to len. So the smallest beautiful substring, if it doesn't contain a string A is lexicographically larger than a string. Okay, so we want the lexicographically smallest substring. That means there are going to be a lot of substrings that have the that have 1 equals to K, right? So we have to return the smallest one. The smallest one. ABCD is lexicographically larger than AB because where the differ is D, right? So let's say we are giving this input 1000 blah 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 blah, and I forgot to start the timer. Sorry, clock. Let's bring it over here. And then 15 minutes as usual. Okay. So the next example we're giving is 100110001, right? And then K is 3. That means you have to find the lexicographically smallest string. This is 1 and this is 1 K3. There are 7 beautiful substrings in this example. The substring. Wait a minute. Aren't these all okay? Okay, there's the substring of this that has 3Ks. There's the substring of this that has 3Ks. There's also the substring of this that has 3Ks, and there's the substring of this. This substring. Okay. The length of the shortest beautiful substring is 5, which is this. Another example is 1101 is 2 because 11, right? Another example is just 0 because they're not beautiful substring. So there is return is a beautiful substring. There's return a beautiful substring, right? There's return a beautiful substring. And then there's return the lexicographically smaller. Return the graphically smallest beautiful substring. So what I'm going to do is I'm going to work with the first. I'm going to work with the first, right? And then find the lexicographically beautiful one. That means they return the lexicographically smallest. All this means is if we start comparing, return the smallest. So this is 1, 2. Okay. So how would I go about this question? Um, so let's look at the topic sliding. Oh, this is a sliding window question, right? I mean, notice that if you consider index I is the leftmost index of a beautiful string, it has only one candidate. You can iterate over all possibilities of the leftmost index I. Take and compare with the shortest and first smallest string we get before index I. Okay, so if this is a sliding window and strings, this is what I would think. First, let's iterate through this. I don't know, this string. We can try to iterate through this string. Start at 1 and keep going till we get the number of lexicographically larger, smaller string. Okay, so we can first loop through all this and start at here, loop, 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 and when it gets to 3, when we've seen that window, we take note of the length of this one. We take note of the length of this. All right. You take note of the length of this. Now we can't really return this, but we can know that from this to this, we saw 3 ones, and then we can take note of the count 1, 2, 3, 4, 5, 6. We can take note of the count, right? And then we can slide the window next. Now the principle of sliding window. Let's quickly check the principle of sliding window. Sorry. Algorithms crash course sliding window. I think I have this documented somewhere. Sliding window. Okay. So sliding window problems are always iterables with ordered items. A subarray is contiguous section of a bigger array. Subarrays have letter about and make it larger. Constraint matrix, numeric restriction of constraints. So here's an example. So okay, so left current answer while current greater than k. Okay, so we're going to keep iterating. Okay, so we're going to keep iterating on this, and then whenever we see that the count is greater than this, we minus 1 and move the item. So we're having 2 now, right? We're having 2, and then we move to this. We move to this, we're still having 2. We move to this, we're still having 2. We move to this, we have 3 now. So how did they arrive at 5? How did they arrive at 5? We arrived at 5. So the idea of this sliding window is that we have left, right, and an answer or current. Okay. So there's a couple of approaches I'm going to take to solve this problem now. There's a couple of approaches I'm going to take to solve this problem now. I have about 6 minutes more. So the first approach I can take is the idea of the sliding window. So we start at 1. We start at 1, and then we have seen 1. We increment the count. Then we loop and we loop and we loop and we loop. We've seen, then we increment the count to 2, and then we loop to 3, and then the count is 3 now, right? The count is 3. When it's 3, then we know that we have seen one like substring, one beautiful substring, right? Now, can we write this beautiful substring somewhere? Can we write this beautiful substring somewhere? And then if it's 3, we write the beautiful string somewhere, then we'll move this one, right? And then now is 2. Yeah. It's 2, and then we move once, and then we move once again. It's still 2, and then we move. It's 3. So once it's 3, we move left. It's still 3. We move left. It's still 3. We move left. It's 2 now. It's 2. There's no more right to move. So we take this 3 and compare all of them to see the one that returns the smallest, right? Now that's the idea I have in my head. I don't know if it's going to work, but I think it is going to work actually. In this case, we start at 1, and then we move to 2, and then we'll see 2 here. Once we see 2, we move the left pointer to 0 and 1, and then we move here again, and we see 2. We move the pointer to 1. We still see another 2, and then we move the pointer to I, and then we return, right? And then we have 2. The first one, the index of the first one is 5. Index of the second one is 2, and then we return the one with the smallest index, which is this one, right? and then return the substring, return the substring, return the substring. So this, for this one, we start at 0. We don't see, we increase. Is 0 is less than 1, we keep increasing, and then yeah. So if I want to write the pseudo code for this, I'll say start by having a for loop. I'll say start by having a for loop through the array. Also place a left point on the right on the array. If number of ones, if the current so remember we're starting at 0, and then we start at 0 and pull left at 0. If x is equals to, if x is 1, add to count if x is 1, add to count true. If count is greater than k, if count is greater or equal to k, if count is greater or equal to k, move the left pointer. If count is less than k, move the right pointer. That's the idea. Move the right pointer. Move the right pointer, right? So there's a lot of edge cases still in my head, but with that analogy, let's start at 1. Let's take this array as is given and try to exploit it. So we start at 1, and then we put count to 1, and on the second iteration, no. On the third iteration, no. On the fourth iteration, no. On the fifth iteration, count equals 2, and then we move 1 and count equals 3. So why count is equals 3 now? We move the left pointer. Move the left pointer 0 to here and here. This is also a beautiful here and here. Now let's take the count of this beautiful substring, right? The count of the first beautiful substring is 1, 2, 3, 4, 5, 6. Is 6. So now count distance is 6, right? Distance is 6. And then we are there. So we moved to 0. No, we moved to the next 0. No, just give me some more time, please. Let's say I just did it for 15 minutes. It's not. So so then we move to the point where we have where this is equals to 3 again. Remember, this is equals to 3 again, and then it's going to look something like this. It's going to look something like this. It's going to look something like this, and it's going to look something like this, and then we can keep moving till we get here, and then return 1, 2, 3, 4, 5, and then we return 5. Okay, so we can try to implement this here. So let's have an answer variable equals 0, and let's loop less than string dot length s plus no x plus plus, and then for each of this, remember we also want to instantiate the left pointer too, which is always going to be 0 for sliding windows. So we want to check if the item we are considering is equal to 1. I don't know. Yeah, equals to 1 is not going to be a number, it's going to be a string, obviously. If it's equal to 1, then what do we want to do? We want to increment answer plus 1, right? We want to increment answer. We want to increment answer. Else, we want to increment the left pointer. Yeah. And then this is where shit starts to get crazy, right? If x is 1, if count is less than k, while we have to have a while something has to keep us going, right? While count, okay, let's say, okay, so I don't know now, but I don't know exactly how to okay, so now we have left here, and then we are going to increment left, but then there has to be a condition that makes us go left or right, right? So remember we start at 0. And then we keep going while this count I don't think we need a while loop though. Oh no. I think I'm missing something up right now. But I think I'm missing something up right now, but so let's understand it again. So we start at left, and then we keep going and keep going and keep going and keep going, right? So the while has to be inside of here somewhere, right? The while has to be inside of here somehow. So what is this is going to do is guys going to keep adding answer. Okay, then we have to have a while loop to check if answer. So to check if answer the length is greater, or keep going if answer this is quite tricky now. Okay, so I want to say keep going, but then there's a while loop, there's a for loop that is going to run through every. Okay, let's take this out for now because I'm getting a little bit confused here. So while okay, so this is the left bound, which is going to start at 0, and this is answer. Answer is going to hold the count, but then if the count, okay, while count is less than, while count is less than k, okay, while count while count is greater than k, greater or equal to k, keep moving left. All right. While count is basically, that's what we want to do. We want to say if the answer is greater or equal to k, greater or equal to k, that means we want to remove something from there, right? We want to remove something from there. While count is greater or equal to k, what's wrong with greater or equal to k? What do we want to do? We want to increment left and remove increment left, but then we don't want to remove. Okay, if okay, so this is what we are going to do now. So we start at, let's just copy this the last time we're doing this analogy. So we start at 1 and write 1 to answer. Answer is going to be 1, and then we keep moving while we keep moving, doing the if, keep moving. So now this, while this is less than, so we remove 1, we remove another 1, we remove another 1, we remove another 1. Okay. If left minus, if s left is equal to 1, answer minus, right? And then if x, if x equals to 1, if xs equals to 1, then what we want to do is answer plus, and then return answer. But there's something we are and then return the maximum of return. In a minute. Okay, this is the for loop, right? Answer equals, and then return answer. Okay, so now what we want to do is the minimum of answer and what the fuck is right? X minus left plus 1. Now this is a lot of guesswork. What's this saying? Why cake? Can't I do greater or equal to? Ah, I see, I see. What is this? Count is not defined. I want to say count. Let's count. How is count instantiated? Equals answer. Answer. Remember, answer. I have 3 minutes more. Time limit exceeded, man. We'll keep incrementing left. Count. Man. I think let's just look at the solutions. What the hell is this? What the hell is this? I'm just take some time to study the question, please. So I couldn't find a perfect solution to this problem, and time is up for me. But I kind of got the initial logic of using a sliding window to go through. Let me just explain it one more time. So we have a pointer here and start a for loop that's going to go through every item here, and then it's going to keep going while the count is equals to 3. We take out the left and keep moving the left, incrementing the left, and whenever the left encounters a 1, we just reduce the count. So for now it's going to be 2 here, it's going to be 2 here, it's going to be 2 here, and then when we hit the 3 finally, we keep removing and removing and removing and removing till we get here, and then we return this guy as the answer. But for some reason, and then for time constraint, I couldn't get it to work. And then the solutions I was saying was quite, well, the solutions I've been saying have been quite not straightforward. So maybe if I have some time later, I'm going to come back to this.